Okay. All right, chapter 1. Chapter 1, we're focusing on genetic mapping. And so the first important thing in chapter 1 is to understand how we measure the genetic distance, right, based on the crossovers. And how we perform this test across to help us calculate the genetic distance between any two loci, just like this. And we need to know the map functions. We have two. So we talked about two versions of the map function, right? One is the Hordane, which is like this, and in the Hordane map function, the C, which is the coefficient of coincidence, something related to the interference coefficient, right? So in Hordane map function, this C is a constant, but in Kosambi, it's not, right? So that's the difference. So you need to understand the difference between these two map functions here. Okay, so I think that's the first chapter. The second chapter, so we were talking about the recombination fraction in different populations. Basically, we focus on two major designs, the backcross design and the F2. And so in chapter 2, the main point is to estimate this, right? The recombination fraction between any two loci. We need to use the data, the experimental data, to estimate this, because this is a measure. The recombination fraction is a measure of the genetic distance. Okay, so you need to know how we calculate this genetic distance, right? Based on the experimental data. And okay, so in the, let's see. So for example, in this F2 family, yeah, that's the table. And so if we are doing an experiment, for example, F2 to measure the genetic distance between A and B, the two loci, gene A and gene B, and because of the recombination crossovers, we can have 4 genotypes in the F2 population, right? And so this represented the experimental data, and we knew. So this is the observation, and this is the expected frequency, right? If there's a crossover between A and B, all right. And so based on this information, you need to know how to get the MLE. This is the solution for the MLE, but you need to know how we set up a likelihood function like this. So for example, like this. So and we get the score function, which is the first derivative, right, for the log likelihood, and set it to 0. And then if you solve this equation, you're gonna get the MLE solution. So you need to know this. So if I give you a question like this, it will be a simple one, not very complicated, but at least you need to know how to use that data, the table, to derive the MLE. Yeah, that's the requirement. All right. So we need to know how to perform a hypothesis testing, right? So hypothesis testing actually is try to answer a biological question or any scientific question. So to answer this question, we have two possible answers. So one answer will be the non-hypothesis, and the other one will be the alternative hypothesis. So we usually put the non-hypothesis on a trial to test if your data support the non-hypothesis or not. So you need to know the logic, the reasoning behind this. Okay, that's for the chapter 2. And So okay, so and okay, so in chapter 2, so we are focusing on the recombination frequency, right? Why is that? Because that's the measure for the genetic distance. So that's why we want to calculate this. And so if you have like a given sample size, so which design will be more powerful, will be more effective? So you need to know the answer for this question, right? So this will give you some clue here. Okay.
Oh,
Yeah, I think.
for that answer, would it be just sufficient to say that we have more samples? Therefore, we have more samples for the F2 design.
We have the same sample size. N is the same, but if this is the case, like N remain the same, so which design will give you better estimation of this R, right? The recombination frequency. So you need to know the theorem behind, right? The logic behind. Okay. All right. So I think this is for the chapter 2. The feature scoring method, that's too advanced, so I will not put any questions about that in the final exam. So don't worry about that. Any questions for the first 2 chapters? All right. Chapter 3 and 4. Okay. So chapter 3, we talked about how we construct a genetic map for more than 2 loci, right? So for example, if 3 loci are linked like this, and so we can perform like the backcross or F2 design to help us estimate the recombination frequency between A and B and B and C, right? And also A and C. So we can do this. And with this information, how one can use this sum of adjacent recombination of coefficients called SAR to find the best order for these 3 loci and construct the optimal genetic map. So this is the major thing for this chapter. So I think this is the only thing for chapter 3. And oops. Oh no. What is this? Sorry. Okay. Okay, and yeah, bootstrapping. We have some like practice code, R code in assignment, right? Just look into that to see if you can use. Oh, what happened? Why is that? Why I keep jumping to here? Sorry about it. Let me close this one. Maybe this one. Why this is the case? Let me close this one. Okay. Sorry about this. Can you see my screen now? Chapter 3 and 4.
Yeah, we see a bootstrapping screen.
Bootstrapping, yes. Okay, so yeah, this is the end of the chapter 3, right? So we have code for this. So just try to look into that code and see if you can use that code to do some like bootstrapping strategy. Okay, that's for chapter 3. And chapter 4 is the multi-loci analysis, the multi-point analysis of the Mendelian loci. Right? I think the major point for this chapter is, okay, so to know how to use this. So for example, how to, based on this information. So for example, if we knew the map of the 3 loci, A, B, and C, and if we knew the RAB, RBC, and RAC, something like this. So if we knew this and how we construct this transition matrix, you need to know what the transition matrix is for, right? And okay, given this, you need to know how to calculate the joint probability that a specific progeny or individual like this. What's the probability that a specific progeny takes the genotype like this? Take genotype 1 at locus A, but 2 at locus B, and 2 at locus C. So this is how we calculate this. And in the final exam, probably you need to use the code I provided in the practice assignment to do a little bit of calculation to find this, given this RAB and RBC. Okay, any questions here? Okay, yeah, that's the only thing for this chapter. And only focus on the backcross because this is the basic, most basic one for the F2. So it's kind of like complicated. So I will not test you on this part. Just focus on the backcross design. And okay. Yeah, I think that's all for the chapter 4. It's quite straightforward. Yeah, those are too complicated, so you don't worry about this. Don't spend too much time on the more than 3 loci here. Any questions for chapter 4? Okay, very good. Okay, a second. Close this one. And, 5 and 6. Okay, chapter 5. So the first thing in chapter 5 is the Hardy-Wimber equilibrium, right? So understand the concept and what does the concept say to us. So what does this Hardy-Wimber equilibrium mean for a population? So you need to understand the concept here. And so if a population, for example, if a locus is following this Hardy-Wimber equation, equilibrium, if this population is a F2, let's say, so you need to know how to calculate the basic things here. So for example, let me show you here. Okay, not here. Okay, so if we're talking about the F2 family, and if any locus is following this Hardy-Wimber equilibrium, then we need to know for any locus, this is a bilinic population. So the P1, P2 means the allele frequency for 2 alleles, right? A and B, big A and small a, and then we know how to calculate. Oh, sorry, not this here. Sorry, give me a second. Okay. So if this population, F2 population, is if any locus in this F2 population is following this Hardy-Wimber equilibrium, then when we use this classical linear regression model to help detect the potential association between this locus and the phenotype, we need to know this, right? How we code this 2 variables here. So the Z variable is for the additive effects, and the W variable is for the dominance effects. And if this is the case, we need to know how to calculate the variance of the Z and the variance of the W. That's easy, right, for the F2 family. And we also need to show the covariance between Z and W should be 0. All right, this is important for this chapter. Okay. Yeah, that's for chapter 5. And the chapter 6 is important because here we try to use different models here to detect the association between the loci and the phenotype. The major thing is to get yourself familiar with the code, R code I provided for detecting the major loci. All right. And here we basically use this model. For example, this is for the backcross design. That's the model. And for the F2 design, so we use this model, right? Because here, this is the phenotype, this is the intercept, and this is the additive, this is the dominance. We use this model for the F2 design. So try to understand this, and we need to know how we use the R code provided to analyze the F2 data using this model, and we can test whether the additive effects equals to 0 or the dominant effect equals to 0. Any questions here? Yeah. I think that's all I want to mention for this chapter. And okay, so in this chapter, we also need to know what the type 1 error is and what the type 2 error is. And this is associated with the hypothesis testing, right? So the type 1 error usually is the alpha. So in any hypothesis testing, we need to set up a significance level for alpha for this type 1 error. The commonly used cutoff is 0.05. Okay. Oh, okay. All right. And okay, so in this chapter, another thing is how to calculate the required sample size, the power analysis. So I think I provided some R code for you. Just practice those code and try to understand what those code is for, and you can also take a look at these 2 examples here. So I could give you a problem like this. So just see if you have like information provided here. So how can you calculate the required sample size, or how can you calculate the power a specific test can achieve? So this focus on these 2 examples here. Okay, so that's all for the chapter 6. Any questions? Because this test, this final exam will be an open book, so you can use anything. And my question, all my questions will be within the scope. I only put questions. So I only test the content from chapter 1 to chapter 8. So within this scope, and everything you can, for any question, you can find some clues or solutions from my lecture notes here. All right, this is for the chapter 6. Any questions here? Okay. And finally, chapter, oops. Sorry. chapter 7 and 9, 7 and 8, sorry. Okay. Chapter 7 is segregation analysis. I don't think I put any questions up for this chapter, but so you probably can ignore this chapter. So I don't think I put any like EM algorithm or mixture model for this chapter. So you can forget about the chapter 7. But chapter 8, let me see, chapter 8, yeah, the genome scan. The genome scanning for the quantitative traits loci. So this one, so understand how we do the genome scanning, and because we have, if we have only a very limited number of the markers, we can still scan the entire genome. Why is that? You need to understand why is that, and so given like the marker like here, if the marker is very close to the QTL, then we can still estimate the possible genotypes for this QTL based on the marker genotype. And then we can still use this linear regression model to help us test the potential genetic effects for this QTL. So that's the basic idea for the genome scanning. And this is how we code the two variables here, right? So for a F2 population. Okay. And the final thing in this chapter is the multiple comparison. If we are handling not just a single locus, we are scanning the whole genome, and we're testing many thousands of SNP markers or molecular markers simultaneously. So we need to know how we handle this potential inflated type 1 error, right? So we talk about like a Bufferoni correction and also like a static correction, and we can also do the permutation test to help us deal with the inflated type 1 error, the family-wise type 1 error. I think, yeah, that's all. So not that hard. Do you agree? All right, any questions? So so this is the scope for tomorrow's final exam. Because I started, so when I started this review, I think not all the students were here. So let me say this again. Tomorrow, for the final exam, you're gonna see 5 questions in your exam. Each question is worthy of 10 points. In the problem number 5, I'm gonna give you an additional question, which is an extra credit question. So if you can figure that one out, then you can earn another 5 points. So that's for tomorrow. And as I mentioned, I'm gonna give you, so for one question, I'm gonna give you, each of you, a individual data sets. You're gonna use some of my practice R code to work on your data and to perform some hypothesis testing. And based on the output, the readout, you need to explain those results to me and make your conclusion whether this locus is a QTL or not, whether this locus is significantly associated with the variability of the phenotype. So this is the problem that is associated with the data analysis. All right, any questions from you? So you can ask any questions. Yeah, take it easy. Don't be nervous. As I mentioned, I agree. This course is a tough one, but my final exam will not be a tough one. So, and it's open book, so you can use the textbook, lecture notes, and even you can search online to find but you cannot talk to each other. Yeah, during the exam, you have to work on your own. Yeah, so that's why. So because we're gonna have the exam through the Zoom, so we need to turn on our camera all the time. Yeah, I'm gonna record everything. Yeah, in case. Yeah. Just you can use any material. Just need to work on your own. Yeah, that's the only requirement. Any question I can help now? Do you have any questions about the any practice code, R code? So we can look into that together. Looks great. I think everybody are confident and comfortable. Yeah, go ahead, Mariano.
Oh, I wanted to ask if you could just once more give an example showing how to take the centimorgan distance from a set of recombinants and parents, like of observations.
You say that again? I didn't follow you. Sorry.
Sorry. If you can calculate from, let's say, two parents and two recombinants, a centimorgan distance, the map distance.
Yes.
If you can just give an example of how, because I know it's not total recombinant offspring over, I mean, recombinant offspring over total offspring. So.
Actually, that's the answer. So if you see some question, let me give you an example here. Okay. So I think chapter 1 and 2. Let me open this one and oops. Okay, so this is how we calculate the genetic map distance between A and B, right, or B and L here, two genes, two loci. So basically, we need to carry out some experiment, for example, backcross design or F2, right? So here, this is the F2 design, because if you cross this one, oh, this is the test cross. Sorry, this is not F2. This is the test cross, right?
Test cross, yeah.
Yeah, you use this double heterozygous parent, and then you cross this double heterozygous parent with this tester, which is the double homozygous, right? Homozygous, and then you can get this 4 possible genotypes. And so with this experiment, you can get some data here, right? That's the data. And from this data, the most important thing for you is to figure out which one, which numbers here are representing the recombinant progeny, right? And if you figure out that, and then it's easy for you to construct this ratio. So the ratio, the denominator will be the total number of the progeny, but the numerator will be the number of the progeny that represent the non-parental type, right? And this is how we calculate R, right?
Yes.
Yes.
Now, if you would use Haldane's on this for, because I did Haldane's on this data, and I got a funny number.
No. I see. Let's see how Haldane. Okay, that's show me how you use the Haldane to get funny numbers. You can let me. I can let you to share.
It's actually on paper, unfortunately.
Oh, okay.
But I used knowing Haldane's R equals 1/2.
Okay, that's fine. Yeah, it's here, right?
Yeah, using Haldane's R is 1/2 parentheses 1 minus e to the minus 2 times the distance, or D.
You mean here or here, right?
The bottom one, yes.
The bottom. Okay, that
Yeah.
in this case, the C equals to 1, which means like the 100% completely independent. Okay, that's fine.
Mhm.
You use this formula to calculate what?
Well, I used the formula R equals that.
Okay.
But in the X, I put 0.10. So 0.10. Or was I supposed to do it on the R?
Okay, you put 0.0 here, right?
Yeah.
X. Okay, that's not the right way to use this whole thing. So okay, that's different. Different issue. Okay, let me make it clear here. All right, that's a good question. So here, so this is how we directly use the experimental data. So this is a test cross data, right? So this is how we directly use this test cross data to estimate this R. Because what's the definition for R? The definition is actually the recombination frequency
Right.
between A and B, right? Between B and L here, all right? So if we have this experimental data, so we can directly calculate this R by using the ratio of the non-parental type divided by the total, right? Number of total. Okay. So this is already the R, 0.1. Okay. Okay. Now let's look at the Hornday. So the Hornday function here is a function that describes the relationship between R and the number of crossovers here. So the X is the number of the crossover is not equal to 0.1. Here, R is equal to 0.1. So, okay. And the Hornday function is actually try to find the relationship here. So this is the Hornday, right? And the Kosambi. So if you look at the X and Y, so here, this is the recombination frequency, which we can estimate it from our test cross. But here, this is additive map distance X. It's not the R. Yeah. So that's why we cannot calculate R using Hornday function. The Hornday function is only try to find the relationship between the R and another measure. So for map distance, we have two types of measures, right? One is through the recombination frequency. The other one is through the number of crossovers between these two loci. So, yeah.
Thank you. That makes it much clearer.
No problem. Any other questions? All right, sounds great. I think it looks like everybody is so much ready for tomorrow's exam.
I was going to ask. I mean, when you said to know how to get MLE, do you want us like to derive it, or like what exactly are you trying to get from there?
Yes, derive it. So, but I will not give you a very complicated question. I will give you a very simple one. But you have to derive it. So, for example, if I give you some kind of data, let me show you. Probably here. Okay, so if you have data like this, then how can you construct your likelihood function? So in this slide, actually you can find some clue here. So this is how we calculate the likelihood, right? Binomial distribution, all right? Because this is horrible. A lot of like multiplication here. So that's why we always handle the log likelihood. The log likelihood here. So this is a log likelihood. The core part is here. This is a constant, so usually we do not worry about this. But so this is horrible. So we just take a log likelihood, and then we will get this from here, right? And once we have the log likelihood, so we know how to do the next step, right? We just do the first derivative for the log likelihood to get the score function, and we set this thing equal to 0. That's very simple, right? And then if you solve this equation, you can get the MLE. So I will give you something like this. You have to follow. I will give you a simple question. You have to follow something like this to derive a simple MLE. Yeah. Okay. Is that clear?
Yeah, that's clear. Thank you.
Sure. Any other questions? Yeah, I'm very happy. It seems like you're very, very much ready for tomorrow. So we're going to start our final exam tomorrow at 9:30. I think 1.5 hours should be sufficient for you. In case you need more time, that's fine. So we can have a little bit more. So don't worry. And so if you do not have any questions, we're going to stop here and see you tomorrow.
Thank you.
Sure, my pleasure. Don't worry, take it easy.
Thank you.
Thank you.
No problem. You're very welcome. See you. Bye-bye.
See you soon.